Greetings and welcome to the 11th episode of PHS Physics SOS. Today I'm going to be going over Part 1 and Part 2 of Chapter 5, which is on work and energy. The first question, which is question 2 on page 171, reads, if a neighbor pushes a lawnmower 4 times as far as you, but exerts only half the force, which one of you does more work? By how much? Now, the concept in this question is that work is equal to force times distance. So let's say your neighbor pushes the lawnmower 12 meters, and you push your lawnmower 3 meters. But you push with a force of 10 newtons, while your neighbor pushes with a force of 5 newtons. That means your neighbor has done a total of 60 joules of work, while you have only done 30 joules of work. So your neighbor pushed it sufficiently further that he ended up doing more work in total. So your neighbor ended up doing twice as much work. The next question is question 3, which says, for each of the following cases, indicate whether the work done on the second object in each example will have a positive or negative value. Question A says, the road exerts a frictional force on the speeding car skidding to a stop. Now, for work to be positive, the force has to be in the same direction as the motion. So in this case, you have a car which is moving this way, but the frictional force trying to stop it is moving this way. So the work done is negative because the movement and the force are in the opposite direction, so negative. Part B says, a rope exerts a force on a bucket as the bucket is raised up the well. Now, the bucket's going up, and the force is pulling up, so it's a positive work done. Part C says, air exerts a force on a parachute as the parachute slowly falls to earth. Now, again, parachute's moving downwards, the air drag is pushing upwards, or air resistance rather. So the work done is negative. Part D says, the earth exerts a force on a bobsled as it moves down the track. So the bobsled's moving down the track, and the earth is pulling it downwards. So even though the bobsled may be moving at somewhat of an angle, if you broke this up into two components, some of this motion would be in the direction of the force acting on it, gravity. So it's still positive work. The next question is question 4, which is determine whether work is being done in each of the following examples. A train engine pulling a loaded boxcar initially at rest. So if we have a train pulling a boxcar, the train is exerting a force in this direction to pull the boxcar, and the boxcar is moving in this direction. So the work and the motion are in the same direction. The motion and the force are in the same direction, meaning that work is done, and it is also positive, but we don't care about that. So the answer is yes, work is being done. Now part B says a tug of war that is evenly matched. Now, so here we have a tug of war with people on both sides and a rope in the middle, and the force exerted by each team is equal, meaning that the net force is equal. And if the net force is equal, if the net force equals 0, and work equals force times distance, and force equals 0, then work equals 0 times 0 distance, so work equals 0 joules. So no work is being done. Now part C says a crane lifting a car. So we have a crane lifting a car. And that looks like a tank, but we'll roll with it. Okay, it's a crane lifting a tank, whatever. And the crane is exerting a force upwards, and the tank is moving upwards. So since we have the movement and the force are in the same direction, work is being done, and again, it is conveniently positive. So not that matters, but we know the work is being done. The next question is question 5, which says, a worker pushes a 1.5 times 10 to the third Newton crate with a horizontal force of 345 newtons, a distance of 24.0 meters. Assume the coefficient of kinetic friction between the crate and the floor is 0.220. And part A asks, how much work is done by the worker on the crate? So the worker is pushing with a force of 345 newtons, and the crate moves 24.0 newtons, 24.0 meters, and we know that work is equal to force times distance. So that's going to be 345 newtons times 24.0 meters, which is equal to 8,280 joules of work done by the worker on the crate. Now part B says how much work is done by the floor on the crate, and you might think, well, the floor isn't doing any work, but if we draw a free body diagram for the crate, it has a downward gravitational force of 1.5 times 10 to the third newtons. I'm just going to write that as 1,500 newtons. And an upward force of, the upward normal force of 1,500 newtons. The applied force of 345 newtons. And the backwards force of friction. Now our frictional force is going to be equal to mu times our normal force, which is 0.220 times 1,500, which gives us 330 newtons. So to figure out the work done by the floor onto the crate, we have to multiply the 330 newtons pushing backwards times the distance it traveled, which was 24 newtons. So work equals force times distance, which is 330 times 24, which equals 7,920 joules. However, since the crate is moving to the right and the frictional force is to the left, the movement and the applied force are in opposite directions, so that means the work done is negative in this instance. Now, part C says, what is the net work done on the crate? So the net work is just the sum of all the work done on it. So it's going to be 8,280 minus 7,920, which is going to be equal to 360 joules of work. The next question is question 3 on page 178. No, it's not. Go ahead, Eric, keep your shit together. The next question is question 3 on page 177, which says, a spring with a force constant of 5.2 newtons per meter has a relaxed length of 2.45 meters. When a mass is attached to the end of the spring and allowed to come to rest, the vertical length of the spring is 3.57 meters. Calculate the elastic potential energy stored in the spring. So, they give us that our force constant of the spring, K, is equal to 5.2 newtons per meter. And they give us that its relaxed length is 2.45, and that its extended length is equal to 3.57 meters. So first thing we want to do is calculate the change from relaxed to extended. So that's going to be our delta x, which is going to be 3.57 minus 2.42, which is going to give us 1.12 meters. You guys can barely see that. 1.12 meters. So now to calculate our elastic potential energy, we need to remember the formula U sub E, or elastic potential energy, is equal to 1/2 kx squared. So now we plug all these in and we get 1/2 times 5.2 times 1.12 squared. And when you plug that into your calculator, you should get 3.3 joules. The next question on page 177 is question 4, which says a 40-kilogram child is in a swing that is attached to ropes 2.0 meters long. Find the gravitational potential energy associated with the child relative to the child's lowest position under the following conditions. A, when the ropes are horizontal. So that means when this child is way the heck up on his swing, and the ropes make a right angle with the vertical line. In other words, when the kid's up here, and here's his starting point, and these ropes are 2 meters long, so down here, the distance between down here and up here, height-wise, is 2 meters. So he's 2 meters up, and he weighs 40 kilograms. So to calculate his gravitational potential energy at that point, we're going to use the formula U sub G equals mgh, or our gravitational potential energy is equal to the mass times the gravitational constant times height, which is equal to the child's mass of 40 kilograms times our gravitational constant of 10 times the height of 2 meters. And when we plug that all in, we should get approximately 800 joules. Now part B says when the ropes make a 30-degree angle with the vertical. So that means here's the kid, here's where he started, and this is 30 degrees. That's actually a very bad picture. So here's where he started down here. So this makes a right triangle, which I'll redraw because that's a terrible drawing, where this is 2 meters, this is 30 degrees, and we don't know what this is. We're going to call this x. So to solve for x, we need to set up a trigonometric ratio, and we're going to use cosine, because the cosine of 30 degrees is going to be equal to the adjacent side, x, over the hypotenuse, 2. And you can't see that again. Draw it down here. So cosine of 30 degrees equals x over 2. So twice cosine 30 is going to be equal to x. And again, make sure you have your calculator in degrees when you plug this in. And you should get 1.73 meters. So that's the distance he is from his starting point. But, or no, that's the distance he is from the top of the swing, just the vertical distance. But we need to know the distance he is from his starting point, which is going to be 2 minus 1.73 meters, which is going to give us 0.27 meters. So to calculate his gravitational potential at this point, I'm going to use UG equals mgh, and you plug in same mass, same gravity, just a different delta H of 0.27 meters. And when you plug that all into your calculator, you should get about 110 joules. Now the last part is part C, which says it wants to know his gravitational potential energy at the bottom of the circular arc. Now, at the bottom of the circular arc, since his height is, they want to know the gravitational potential energy relative to where he started. And since at the bottom of the circular arc is where he started, the delta H is 0 in U equals mgh, meaning that the entire quantity becomes 0, and that his potential energy, with his gravitational potential energy relative to his starting point, is 0. The next question is question 3 on page 178, which reads, a pinball bangs against a bumper, giving the ball a speed of 42 centimeters per second. If the ball has a mass of 50.0 grams, what is the ball's kinetic energy in joules? Now, the first thing to note about this problem is that the book writers are dicks, because they gave you the units in centimeters per second in grams, whereas joules, the unit joule, is kilogram times meter per second times meters squared per second squared. And if you use the formula K equals 1/2 mv squared, your mass needs to be in kilograms and your velocity needs to be in meters per second in order for you to get these units up here. So first thing we have to do is convert units. So it gives you the speed of the pinball is 42 centimeters per second. Now we change that into meters per second and we get 0.42 meters per second. And the next thing they give you is 50.0 grams, which is equal to 0.0500 kilograms, which is our mass. Now we can plug these two numbers into K equals 1/2 mv squared. So we plug in our numbers, plug it into our calculator, and we get 4.41 times 10 to the negative third joules. Sorry, I'm a little sick here. The next question is question 4, which reads, a spoon is raised 21.0 centimeters above the table. If the spoon and its contents have a mass of 30.0 grams, what is the gravitational potential energy associated with the spoon at the height relative to the surface of the table? Again, another annoying question, because the first thing we have to do is convert units. So 21.0 centimeters is equal to 0.210 meters, and 30.0 grams is equal to is equal to 0.0300 kilograms. Now if we plug in all our numbers and plug that into our calculator, we get that the gravitational potential energy of the spring is 0.063 joules. The next question is question 5, which says a 65 kilogram diver is poised at the edge of a 10.0 meter high platform. Calculate the gravitational potential energy associated with the position of the diver. Assume the zero level is the surface of the pool. Now this is a very simple gravitational potential energy problem, so we just plug in our numbers and we have a mass of 65 kilograms, gravity is 10, and h is 10, so we just have 10 times 10 times 65, which you should be able to do in your head, and you should get 6,500. The next question is question 6, which says, what is the kinetic energy of a 1,250 kilogram car moving at 45.0 kilometers per hour? Now, the first thing we have to do is convert 45.0 kilometers per hour into meters per second, and now we just plug our velocity in meters per second into our kinetic energy formula, which is k equals 1/2 mv squared. So we get k is equal to 1/2 times 1250 times 12.5 squared. And when you plug that into your calculator, you should get 9.77 times 10 to the 4th joules. The next question is question 7, which says, the force constant of a spring on a child's play toy car is 550 newtons per meter. How much elastic potential energy is stored in the spring if the spring is compressed a distance of 1.2 centimeters? Now, for the first part of this problem, we either have to convert our spring constant into newtons per centimeters or convert the distance into meters, and I'm going to convert the distance into meters. So 1.2 centimeters is equal to 0.012 meters, and now we just plug that into our potential energy of a spring formula, which is U sub E equals 1/2 kx squared, which is going to be equal to 1/2 times our constant of 550 times our x of 0.012 squared. Now when you plug that into your calculator, you should get 0.040 joules. The next question is question 8, which says a 25.0 kilogram falling object strikes the ground with a speed of 12.5 meters per second. If the kinetic energy of the object when it hits the ground is equal to the gravitational potential energy at some height above the ground, what is the height? Now, this may sound really confusing, but what it means is if you have an object that's dropped from up here and hits the ground down here, then the kinetic energy at this point is equal to the gravitational potential energy at this point, and it wants to know the height. So we know that in these two constants, the one that we can figure out height from is our gravitational potential energy, which is equal to m times g times h, and is equal to, and if we set that equal to our kinetic energy, which is 1/2 mv squared, well, the first thing we can do is cancel the m's. So now we have g times h is equal to 1/2 of v squared. So now if we divide by g, we will get h equals v squared over g, and if we just plug in our numbers that they give us in the problem, you'll get 12.5 squared over 10, which is equal to 7.8 meters. Thank you for watching this episode of PHS Physics SOS. I hope you found it helpful, and if you have any further questions, please leave them in the YouTube comments below, or on the Facebook group, or text me, or message me on Facebook, or get a hold of me on Skype, or get a hold of me at school, and I will do my best to help you. Thank you for watching.